Professor Bai for the invitation to give talks here. So this is a series of talks. What I would like to do is to talk about, to give some introduction, at least to lay some foundation for you to read the papers of Comets. So what we do is basically is the result of Professor Pierre Comets. So what he did is this so-called p-adic local Lagrange program. So certainly I cannot finish this in 10 hours, and actually his paper is not published yet and is only available online, and you need a lot of work to study this. I think, yeah, so there are like 7 to 8 preprints in his webpage, and the longest one, I think this is this one. This looks like a book, is a paper of 200 pages, something like this. So I just want to say, okay, it gives a little bit about this, and then maybe some about p-adic L functions, and then so that there's some applications for this instead of just to finish this big program. But say the significance of this problem is like this. If I draw a diagram, you can say, this is the p-adic local Lagrange, and then you have this so-called Fontaine-Maisel conjecture. This is a big conjecture, but then this is if you just look at this n equals 2 case. So by this, so it's almost done. So by Marquesin, so basically prove this Fontaine-Maisel conjecture. This is a big conjecture, and then from this Fontaine-Maisel conjecture, you can also have, then you have this cell conjecture. Certainly, the order is not like this, right? We all know this. This is done by Carl and Winterberger. So this is already done, but this result of Keystone relies on Comets results. So Comets have to finish this, and then before they can claim they finished this proof of Fontaine-Maisel. But you know the cell conjecture, you certainly know, and then you know from the cell conjecture you have Shimura Taniyama. And from Shimura Taniyama, you have this Feynman-Lars theorem. So certainly, so that means that this is a big result anyway. And so what I'm going to talk. So in the first part, I would like to talk about these spaces of functions. Continuous functions. Over ZP. So probably like these 2 hours, I will just talk about this. The second part, I will probably talk about distributions and measures. From this, you can have all these p-adic L functions. For the notes, I so just handed out. So basically, I talked about this distribution measures and then talk about p-adic error functions there. So probably I will not talk about p-adic error function in these talks, in these 5 talks, but certainly the first 2 I will talk. And then the third part is about phi gamma modules. And the p-adic representations. So this is those theory of Fontaine and Fontaine comets. Or maybe just comets, Berger, and or other guys like Kedelaya or other people. So this maybe is talk number 3, and the last 2 talks, if we have, I will explain a little bit about in the introduction part of this p-adic localizers. So 4 plus 5 maybe is comets. So work. But certainly these 2, the first 3 also contains a lot of comets work. So he did a lot in this subject. So first we have all these notations. I think you already know QP, ZP. So this is easy. And we also have this CP. This is you take QP, and then you take the algebra closure. But then this is not complete, right? So you want to take a completion. So you get this field we call CP. This is a p-adic version of C. And then you will also have, say, we have a p-adic evaluation, VP. So VP, we just means VPP is 1. So you have this evaluation, VP. And we have an L is always contained is in CP, so it's a field. We will introduce a lot of notations later, but now at first we just have these kind of notations. Oh, so if we have L, then we have OL, so it's an integer ring, and then ML, and then KL. So it's maximum idea. So if L over QP is finite, then we will also have a uniformizer pi L. So pi L is uniformizer of ML, the generator of ML. So that's the notation, the first group of notation we have. To read the papers of comets, so there are many hard points. So first is in French, so you have to study French. And the second thing is there are lots of notations. So first you need to know the rule of those notations, and then it should be easier because even is in French, is in very, very easy French, and then it's very clearly written. But the hard point is it's hard to ask him to write in English. He gave a talk in Tsinghua in 2004. So we have those notes, and you can find it in my webpage. So, but he didn't want to finish it as a book, so he just leave it there. So I don't correct some mistakes there. Okay. So first we want to say, okay, it's about space of functions over ZP. I think there are some students here, so many students want to say, okay, if it's analytic number theory or it is algebraic number theory. But at this moment, it's hard to see which is analytic, which is algebraic. Certainly the results, what we are talking now, are very algebraic and also even geometric. But the method here is very analysis. Say in this talk is basically just p-adic analysis. So first I will talk about p-adic Banach space. So we have L. So B is an L space. So L vector space, and it's called Banach. If we exist a semi-valuation VB, for example, when B goes to R intersection plus infinity, satisfying the properties. So there are three properties. So VB x is plus infinity if only if s is 0, and then VB x plus y is bigger than or equal to minimum of VBX, VBY, and the third one is VB lambda x is VP lambda plus VBX. So here lambda is contained in L. So if you say lambda is contained in B, certainly then it's a valuation, right? But here, so this lambda is just in L. So if we satisfy these three properties, we say it's a semi-valuation. So if we exist this kind of semi-valuation such that B is complete, under the valuation. So but under valuation, we can also under the metric. So we can say the metric is just P to the minus VB. Okay. So this is the same thing as a Banach space over real numbers. You say VBX is plus infinity, just means the metric is 0, right? So Banach space is complete norm space, right? So its norm is 0, equivalent to x is 0. So we have this. This is the definition. So we get some examples. So the first example, we have this L infinity I L. So what is this? This is just say all this is the same thing. So N is contained in L and bounded. So this is the, and we can define the evaluation. We just take the so because this is bounded, then this is bounded below. So this you can always find the minimum of this, and then you can get this one. This is the same thing as in the Banach space over real numbers. Again, it's the same thing. And also we can have this L infinity 0 IL. So still now you say, so first is contained in this such that AN goes to 0 as N goes to plus infinity. So that means converges. But this, you can also say AN goes to 0, this is equivalent to VP AN goes to plus infinity. So we can all have all these kind of notations. Okay. So the third one we can work. So I is just an index set. So should it be contained in I? Sorry. So it's n containing I. And then you will have trouble. So what does this mean? N goes to infinity. So you need a little bit careful about this if you just index set. So you can use calculus. Say, for example, given any c bigger than 0, so this is equivalent to given given A, there exists n, no, say given c bigger than 0, the number of an less than c, bigger than c, is finite. So this is for any c bigger than 0. So it's finite. So that's the meaning about as n goes to infinity, because you don't have infinity here. So it's indexed I. Okay. So you have this kind of notation. So we can also have instead of I, instead of L, you can choose any B. If B is a Banach space, you can also, this is also a Banach space. The first thing what we have is especially this. So this is a continuous function over dp with values in L. So, but this one you can also define the VC0. So if function f, I just say x is contained in Vp f of x. So then this is also a Banach space. So Banach space, this kind of p-adic Banach space is very similar to this Banach space over R. So you have many properties. It looks like the same. So that this kind of proposition. So we have one is basically it's just open image theorem. In Banach space. So what is open image theorem? So if you have f is b1 goes to b2, continuous, linear, and bijective. Then f negative one is also continuous. And we also know if it's continuous just means it's bounded, right? So there's a Banach space, the property. The second one is so-called Banach Steinhaus. What is this? Is say if you have all this f of n, and it goes to f, say pointwise, and fn continuous, then F is also continuous. So these are classical theorems from Banach space that is still true in this set. But there's another one is not true with this Hahn-Banach. But you need to check the book what is Hahn-Banach theorem. So this is the question marks here. Now we have this, so we need to define a basis. So you might not, we define called Banach basis, but here we change the name, so we call orthonormal basis. So if you have like EI is called, so this is the same thing as in the notes. In the notes is called the Banach space. So this orthonormal basis of B. If we have this, if we have, we can define L I, we can go to B, we have this EI, so we have AI, we can go to summation AI EI. It's an isometry. Okay, so isometry means it's not only isomorphism, but also it keeps the distance invariant. So it's isometry. So if we can just say a Banach basis, then this is an isomorphism. So we just change it a little bit. So what this means, this is called orthonormal basis. So this is equivalent to the notation we have. So first, for any x is in B, they exist, all this AI L infinity 0 RL X AIEI. So and the second one is we have this VBX is always VP AI. So this is isometry means the second one. The first one means is isomorphism. Okay. So the other thing here you can see is, in particular, you can see what is this? This is always 1. This is always 0. Yeah, this is always 0. Okay. So that's the definition about orthonormal basis. Basically, what we need in this Banach basis, in Banach space, we need this orthonormal basis. And we also need something about dual and also other. So first thing about proposition is about we have all Banach space, all Banach space have Banach basis. So just means if you just want a Banach basis instead of orthonormal, then you can always find it. The second one is so B has an orthonormal basis one necessary condition is because of the second part, you can see if so you must have this, right? Otherwise you cannot. The second part, the second one cannot be satisfied. But this is also a if and only if condition, so this is the same. And in this case, how do you note B0 is X contained in B? Then how do you check this is a basis? So is a basis is also normal. If only if you have so first you just say this is a basis of B0 over PB0. So you can see it just means this must be in B0 over L over KL. So KL, we know this is just a pi. Oh, this is not P. Sorry, it's pi L B0 because we talk about L, so it's pi L. So KL is we have is OL pi L. Right. So that's a proposition. I think this is easy to prove. With this, we also have the dual of Banach basis defined. So it's dual of Banach basis spaces. So if we have B, now we define this B star. What is B star? B star is just we just like this is BL. So is F B goes to L continuous. Of course linear. So we always get this linear and continuous. We just let B star is this. So this is a dual, and then we B star F we can define as in B, but it's not 0. VPF of X minus VBX. Then B star is Banach. So this is another Banach space. So if you give it one, you can get the dual because we need to use the dual. So give an example, and you can prove is this L infinity RL is nothing but L infinity 0 IL and take the dual. You can take the dual and you can get this. Okay. So this about dual. So the last thing we want to talk about is about tensor product. So tensor product. If we have two algebra, even like two L space, two module, we can define the algebraic tensor product like this, right? But here we are talking about Banach space. Banach space is always complete. So if you want the metric to be complete, so this tensor product we need to say is topological tensor product. So first take the algebraic tensor product, and then we take the completion. So this is so-called topological tensor product. So what is the valuation of this? So if you have say like x, you can get like xi times yi, right? So if you have this, and then you need say v a tensor b x, and then you need to get is just should be v a xi plus vb yi. You need to get this. So this is topologically tensor product, and then you can make all this kind of tensor product. But if you have tensor product, say we can have if you have this is one thing we need. That's quite useful. We will use this again and again. Is this? If I have L infinity 0 I L, we know this certainly has an orthonormal basis. This is easy to find, right? And then you can take this. This is nothing but B. Okay, so this kind of thing we need to use is many times. So corollary of this, say if we have L intersect K and in CP, for example, and then B is L Banach with orthonormal basis. Say EI, then you can take this, you can extend it. So this is a K Banach. So it's K vector space instead of L vector space, and then it was the same. So it's the same orthonormal basis. Okay. So the other ones, what we will do is in this talk, we will have say we need to find this. We just need to find this, right? But actually, what we'll get is like this one. We first find this. If we can find the orthonormal basis of this, and then because of this corollary, you can always tensor product. If this is finite, then you don't need to take completion. But many times this is not finite, so you need to completion. This is always this. So a basis here is the same basis here. So that's what we're gonna study. And so for Banach space, we just need all these facts. Now we move on to the second topic. So the second topic, 1.2, what is this continuous function? So it's over ZP. So what is continuous function? So what I said, we need to study this. So at least we want to find a basis for this. And if good is also normal, that's the best. And this is what we want to study. And we also know this V C0F X. So we know this CP is compact. So this you can always achieve. So even you don't need the infimum, you just take the minimum, because this is compact. You can find enough thing to cover it. And with continuous function, this is easy. So the first thing is we define this xn. Well, this is just the binomial number. So it's 1 if n is 0. X minus 1, x minus n plus 1 over n factorial if n bigger than equal to 1. So what is the Korean definition of n, including 0 or not? No? So here we always 0 is contained in n. Okay. Okay? So this is the French definition. But I think now in Chinese high school books they also use this. I don't know. Yeah. So we have this, okay? So the first number is we see 0 xn. So this function is 0. If we want this to be a basis, so as I just said, a basis, especially also normal basis, the valuation is always 0. So, but this number is easy to prove. So since this is easy, so I just prove it. Okay, you take x equals n, you get n is 1. The valuation is 0. Take x is contained in n, then xn is contained in z anyway. At least it is contained in z. So from these two facts, so from here you can VC0 xn is less than or equal to 0 because you take the minimum of this. But this is one of them, this is less. And this is contained in Z. And also we have n instance in ZP. If you look, because this is continuous, so just means it's always bigger than or equal to 0. Right? Because this is an integer. The integer's valuation is always bigger than or equal to 0. And then this is less than or equal to 0, and this is bigger than, so you get this equal to 0. Okay. Now we get this classical theorem of Mahler. So this, I think many of you made it before and know how to prove it. So this Mahler theorem is that if f is contained in C0 dp L, so you can replace L by QP. Then we can write f uniquely as f a and f xn. And this A and F and contained in N, this is contained in L infinity 0 and L. So even you can say is, yeah. So what does this mean? This means this is unique and this is this. So that means you have isomorphism of this one. So you get isometry of this one to C0 dPL. So that means Xn is an orthonormal basis of C0 of these continuous functions. Okay? So what is ANF? Moreover, we can get what is ANF? ANF is nothing but you can work on it. So it's I 0 to n minus 1 to the power I, and n choose I, and f n minus I. Okay. So how do you get this? You should get this is by iteration. So some iteration is if we have f of x, we get f0 of x is f of x, f of k plus 1 of x is f x plus 1 minus, and then you can let A and F is just 0. We just take this. But this, because of the iteration, you can fkx, you can get it. Fnx, this is nothing but I n minus 1 to the power I n choose I f of x plus n minus I. Okay, so this is the definition. Okay, so the Mahler theorem basically says this is also normal basis. So you can get a corollary is for any b. Here you use L, but you can use B. So you can see ZP D is ZP QP you can always get this because of or if you don't want B, you want L, you just like this because we only need L for any L. Okay. Because this XA is defined over QP with value in QP. Okay. So to prove this theorem, this is easy to prove. What we prove is we let B is just all this F. We let this is called, for example, we get AF, we just say is ANF. So AF is contained in L infinity 0 and L. So we want to prove this B is actually this, right? But first we just let B exist. And then B is closed. It's closed in C0. And we also have, so first, you have for any A is in this, we let f of A is ANF xn. So this is containing C0. Now you can check. You can check. You can check f of A. So if you define f of A this, it's nothing but A. So that means this is surjective. So certainly means B is surjective. And moreover, you can find it's not only surjective, and also moreover, you can check with C0, f of A is just with L infinity A. Why? Because, so first because from here, from this definition, you can see this one is bigger than or equal to this. Because you take the valuation and then you use the property of valuation. So first you get this one is bigger than or equal to this. But because of this, and also this property, so if you take the valuation of this one, certainly, yeah, it's bigger than or equal to this side. Okay, so you have two side inequality, and then you must get an equality. Okay, so that's why you get an isometry here. So here, if I write down like this is always an isometry. So the first thing you get this surjective and also is isometry. So the second one, what we get is injective. Injectivity. Now this is easy. So if AF is 0, if from here, if AF is 0, just means ANF are all 0, and then from here you can, by induction, you can get Fn is 0, then for n is contained in n. But this stays in ZP. So we get F is 0. So that's injectivity. Okay. So you get surjectivity, you get injectivity. So we only need to show B is C0 and ZPL. Just means this B actually cover everything. But this one, there are two ways to prove it. One way is you use this number, the same thing in my notes. So the other things we need to talk about locally constant function. So I will just leave after I finish locally constant function to prove this is actually the case. So maybe we just have some break.